We are on to our fourth type of reaction. We had the combination or synthesis reaction, the decomposition, the single replacement, and now the double replacement. Double replacements often involve an exchange of positive ions between two compounds. It is like a double switch or a double replacement. In a single replacement, we always had one element that was single, and it was replacing an element in a compound. Now you're going to have two compounds, and they'll each kind of switch an ion. They usually form something called a precipitate, a gas, or a molecular compound like water. We should mention precipitates are solids that form from a reaction of two solutions. So you have two aqueous solutions, things that have been dissolved in water. You mix them together and you get a solid. The solid is called a precipitate. So it doesn't necessarily mean to rain in chemistry. It refers to a solid, something that will form out of your solution and kind of drop to the bottom of the beaker. This picture here shows a good example. It's a really cool reaction where you can take two aqueous solutions. We've got some potassium iodide and lead nitrate, both aqueous. And now remember back in the day when we were talking about intermolecular forces and like dissolves like, how polar substances dissolve in water because water is polar, and anything else with a charge then is very attracted to water molecules. Yeah, that's exactly what they're kind of showing with these particle models now, where if I have a solution of potassium iodide, the potassium ions and the iodide ions have kind of separated from each other, and they're swimming around in the beaker covered with water molecules. And if you look closely, you can kind of see that the water molecules are in the proper arrangement. That if I have a positive ion like potassium, it should be the negative oxygen end of the water molecule that surrounds a positive ion. And then it's opposite for a negative ion like iodine. Then I've got the little positive hydrogen end of the water molecule surrounding a negative ion. Now the same is true of the lead nitrate solution. If it's aqueous, it's dissolved in water, and then it just means that the ions have separated. So I'm going to have individual lead ions, and for every ion of lead, there would be two ions of nitrate, and they have their little shells of hydration. All those charged ions are covered with water molecules. Okay, so in a double replacement, you're going to start with two compounds. There are going to be two solutions. There'll be two aqueous compounds. And you just have a double switch. So the two positive ions, the lead and the potassium, just switch spots with each other. A double replacement. So that now on the product side, the lead will be bonded to the iodine and the potassium will come over with nitrate. Now notice that the formulas are a little different. When potassium was with iodine, it was a 1-to-1 ratio. Now on the product side with lead and iodine, it's a 1-to-2 ratio. Yeah, whenever you make a switch, whether it's a single replacement or a double replacement, switch the ions or the atoms, but then whenever you make a new combination, you've got to check the charges. So for example, when potassium is with iodine, it's a +1 -1. When lead is with nitrate, nitrate is -1. Since there's two of them, the lead must have been a +2. Well, often, let's get this out of there. Often the charges stay the same from one side to the next, but again, the ions are just with a different partner. So now I'm going to have the lead with the iodine. And so, yeah, it's a +2 -1. That's why there's two iodine now. Or when I have potassium with nitrate, it's +1 -1. Now it is a 1-to-1 ratio. So be really diligent about checking your charges anytime you make a new compound or a new combination of ions. And then obviously we balance from side to side to eventually make sure that there's the same number of potassium, iodine, lead, and nitrate on both sides. But here's kind of a good visual of this reaction too, that you've got these two colorless solutions and you mix them together and you get like this cloudy yellow solid. That cloudy yellow solid is the lead iodide. It's just that sometimes you make a combination of ions that are really strongly attracted to each other. In this case, it's the lead and the iodine, that when they come together, they form a bond, a pretty strong bond, so that they'll actually drop out as a solid. Whereas the potassium and the nitrate, they stay aqueous, which just means that they're still ions swimming around in the solution. But it's kind of a good visual of what this reaction looks like. You've got that solid form. It's like a cloudy yellow solid. So in number 20 then, let's see if we can do one of these. Use the model for double replacement reactions to predict the products of the following reactants. Circle the ionic solution and underline the other compound, which I think they're referring to the products. Okay, so I've got potassium hydroxide, an aqueous solution of potassium hydroxide, mixing with HCl, which is the formula for hydrochloric acid. Okay, so I kind of like to go in and put charges on all my ions. The calcium is a +2, hydroxide is a -1. All those polyatomic groups you'll still find on the chart on page 98. So have that bookmarked, flip the corner over. You're going to use that chart quite a bit. Hydrogen is a +1 and chlorine is a -1. Also, I'm hoping that by now you've got all these charges marked in on your periodic table for the main group elements, like all of the group 1 alkaline metals are +1. All the group 2 alkaline earth metals, like calcium, are +2. Transition metals, we would have to have a Roman numeral. And then, when I get over to like chlorine, all the halogens are -1. That should be marked in on your periodic table, and man, is it going to come in handy. Okay, so I've got the charges in, and it just kind of helps me know that I'm going to switch the two positives. Now, often the positive ions come first in each compound, so you could just switch the first ion of each compound, but eventually I'm going to want to know the charges. So I kind of like just putting them in right away. All right, so now here comes my double replacement, my double switch. I'm going to kick out hydrogen and bring that over with hydroxide. And then calcium is going to come over with chlorine. So to start with, we just make the switch. Switch the two positive ions. But now I made new combinations of ions, and I must check the charges. So that's why I like just having the charges in, because I'm going to need them anyways. Hydrogen is a +1, hydroxide is -1. Calcium is a +2, chlorine is a -1. Well, my HOH is neutral, but I'm going to need 2 chlorines here. So I get a +2, -2. Awesome. And now the last thing, well, I should say one of the last things I would do is balance it. Alrighty. So 1 calcium, 1 calcium. Looks like there's 2 hydroxides. Here's my hydroxide, and then here there's 2 of them. Now I can't change the formula on the product side because it's a neutral particle. So if I want 2 hydroxides, I just have to go all the way out in front. Now that also gives me 2 hydrogen, 2 hydroxides, 2 hydrogen. But that's okay, because I'm going to have 2 hydrogen on the reactant side anyways. I'm also going to have 2 chlorine on the reactant side, and I've got 2 chlorine on the product side. The balancing part should be the easiest part of any of these reactions. Like once you get the reactants and the products, once you get all those formulas written correctly, the balancing should take you no more than 60 seconds, 1 minute. And if it's taking you more than 1 minute to get an equation to balance, check your formulas. Check your charges. If you would have forgotten like that 2 behind the chlorine, the whole thing won't balance and it's going to drive you bonkers. So double check those charges. Be real good about like putting the charges in. So I know I got my formulas right. All right, there she is. It's balanced. Now the last thing that I usually do is put in the phase symbols. And so it might help to know that HOH is also known as water. Often when we're writing these balanced equations, it might kind of come up as HOH on the product side. Hydrogen has bonded with a hydroxide. But HOH, hydrogen hydroxide, is commonly known as water. So water is a liquid unless I'm told otherwise. And now they're telling me that there is an ionic solution. Circle the ionic solution and underline the other compound. Well, if I know water is a liquid, that's not an ionic solution. Ionics contain a metal. So that's going to be my calcium chloride. And so I'll put that in as a solution or aqueous. It's kind of what they mentioned earlier here, that often with these double replacements, you'll get one product that is an ionic solution, so something aqueous. The other product could be a precipitate, a solid, like this example with the yellow solid. Sometimes it's a gas, or some kind of a molecular compound, such as water. Molecular compound just meaning like something covalent. There we go. So now I've got my equation finished. And if I wanted to follow the rules, when it says circle the ionic solution, that'll be this guy. And underline the other compound, that would be my water.